All right, measurement. Okay, in Physical Science 20, we need to talk about measurement, how to measure things, what measurement is, how exact we need to be, and that sort of thing. So let's learn a little bit about measurement. In math, numbers are called figures, okay, so, or digits or figures. In science, we want our work to be as exact as possible. So what this means is that we want to use the best measurement possible. The most exact measurement includes only significant figures. Okay, so we're going to talk a lot about significant figures coming up. More on this later. So whenever we take a measurement, there is a certain measure of uncertainty about the measurement. Okay, uncertainty. Now, I'm not sure about the blanks that you guys have on your notes here. I'm going to highlight some of the important words. In the drawing below, this is very important now, pay attention. In the drawing below, the same piece of metal is measured using two different sides of a ruler. Okay, so here's the metal strip that's measured on this side and on this side. So if we kind of cut this ruler in half, okay, and we understand that if we were measuring this metal strip right here, from the front to the back, and all we had was these gradations here, okay, or these little tick marks to measure the length, then we would be restricted in the exactness of our measurement, okay? Because, for example, all I know is that this metal strip is a little bit bigger than 5. That's all I know. I would have to guess after that. But on the underside here, if I was to look at these gradations here, these little tick marks, I can actually see, hey, I know exactly where 5.1 is. I know exactly where 5.2 is. So I know that the metal strip is between 5.1 and 5.2. So I can be a little bit more exact. So the exactness of a measurement depends on the measuring tool. So let's read a little bit what you have on the notes underneath here. It is easy to see that the measurement on the bottom is more exact. The measurement on the top is 5 centimeters, and then we don't know what the other digit is. We know 5, we don't know beyond that. It's maybe 5.1 or 5.2 or 3, we're not really sure. While the measurement of the bottom, on the bottom, is 5.1 something. So I have an extra digit that I can be more exact with. All right? But we also know that it is some amount longer than that. So this important information, if you want the measurement to be as accurate as possible or exact as possible. Okay, so in this example, what you might want to draw on here, right on here, okay, is that this would be 5, and we would guess one more digit. So you can go to one uncertain digit here. I would say maybe 5.2 centimeters. That's what you would guess based on what you can see right here. Okay? Now, on the bottom, if we look at the bottom, I can see, and I'll zoom in there on this. Okay, I'll zoom in. Whoa. So I can see that this is 5.1. 5.1. This is 5.2 right here. And I can see that the metal strip is certainly between 5.1 and 5.2. So I can state this as 5.1, and then it's going to be, I can go one more digit. And when you're taking measurements, you can always go to one uncertain digit. You use all the digits that are certain, and then you can put one more in there as your guess. And it's always understood that every measurement has the last digit is the uncertain digit, okay? So I can say, I'm going to say that's right in between there. That's right in between, so I'm going to say 5.15 centimeters, all right? Now those are it's really thick because I zoomed in a lot. So this measurement is more exact than this measurement up top. Got it? Comprehendo? Understande? CC? Yes, I'm bilingual. Multilingual. I can speak English and Mexican. I know that's not a language, I'm just joking. And I can speak gibberish. Okay. Where were we? Okay, in the bottom measurement, we know for sure it's 5.1. We can go a little bit longer than that. Okay. significant figures. Now we're gonna hear a lot about significant figures. Okay, sometimes the textbook's gonna call it significant digits, but sig figs is the abbreviation, sig figs. Okay, now significant figures are really important when we're talking about using multiple measurements. Think about this. Okay, if you have a chain that is linked together, right, and we have one link that's kind of like a little shoddy and rusted and broken, okay, but all the other ones are good. You guys have heard the old adage that the chain is only as strong as the weakest what? Link, right? So this chain, these links are pretty strong right here, but this one's pretty weak. So the whole chain will be only as strong as the weakest link. You've heard that before. Now, in the same sense, when we talk about different measurements in science, the weakest measurement or the least precise measurement will determine the precision of our calculations. Okay, so that's what we're talking about. And that's why it's important to note the sig figs or the significant figures in all of our measurements. Okay, let's read on here. Whenever we give a measurement in science, we should always give all of the digits that are certain plus the first estimate. So I just talked about that. The first uncertain digit you can write in your measurement. We call all of these digits in the measurement significant digits or significant figures because they are the important ones in the measurement, as I mentioned here. So let's say we are adding some things together and I have masses of different things. I have 5.12 grams, and I have 5.339 grams, and I have 5.1 grams. Okay? The precision is governed by this weakest, I'm going to say weakest in quotes, by the least precise measurement. So the sum here, when we add all these up, can only have two digits. It can only have 2 digits. This exactness and this exactness doesn't matter because it's trumped by this exactness. Okay, it's the lowest one. It's the weakest link right here. All right, so how do we determine how many significant figures measurements have? Let's work on these some of these rules here, okay? And how many of you remember doing this before in any science class before? Yeah? Okay, so you've seen this before, hopefully? About half of you raise your hand? All right. All right, well, it's not that hard. In order to maintain the significance of a measurement, there are some rules for working with these numbers and for reading the measurements. So when you see a significant figure, remember these rules. All non-zero digits are significant. So anything that's not 0, you would count that as being significant. Okay, so anything that's 1 through 9. So in these measurements, significant, significant, significant. This has 3 significant figures. In the second one, they are all significant. That has 4 significant figures or digits. This one has 2 significant digits. Notice that this one has 2. It's the lowest. Okay. The second rule, all zeros, so we know about non-zero digits. What about 0 digits? All zeros between non-zero digits are significant. So what that means is if you have a number like this, 12,003, well, this is significant, the 1, the 2 is significant, and the 3 is, we know that from rule 1. The zeros are always the ones that are in question, and if they are sandwiched between any other significant digits, they are also significant. So this has, this has how many? 5 sig figs. And you will see me abbreviate sig figs SF''S. Okay? On tests, if you state your answer without the proper sig figs, you will see this on your test. Minus 0.5 sig figs. Or minus 1.5 or whatever. So you will get marks docked off if your answers, you don't pay attention to the rules of sig figs. Okay?
So if you always, why would you take the number of sig figs from the most inaccurate measurement?
Yeah, because, okay, so why would you take the number of sig figs from the most inaccurate or the least precise? Is because of this right here. Because the weakest link, think about that. You can have some really strong links, but the value of this chain is governed by the strength of the weakest link. Just like this can be a really accurate measurement, but when you now add this measurement or you multiply this measurement, let's say these are all multiplied, okay? If you multiply all these together, then your answer might have 5, 6 decimal places on your calculator, but you know that your actual measurement is not that precise, because this right here is the least precise. So you can only use this one as in your final answer.
Do you round or do you?
Yeah, we'll get practice with all this. Yeah, good question. Yeah, we'll practice with this, no problem. Let's first understand these rules and get back to rule 3, okay? So zeros to the right of a decimal point and after non-zero digits are significant, okay? So if you have a number like 1, 2, 3, 4, decimal, and then you have all these zeros after the decimal point and after these non-zero digits, they are all significant, because that tells us that, hey, this measurement is obviously precise or accurate to 1, 2, 3, 4 decimal places. By putting those zeros, you're saying this is a very precise measurement. You can't just go ahead and throw zeros after a decimal place and think it doesn't mean anything. It means that you are sure that it's 0, 0, 0 at the end, like 0.000, right? Yes, question?
So in this like scenario, there
Mhm.
could be a 1 after that last 0, but you don't
Yeah.
know.
Well, there could be a 1, yeah. So
It doesn't have to be. Right?
okay, there doesn't have to be. No, doesn't have to be. So what this is saying is that, let's say that you're stating this as a measurement that you took in the lab. What you're saying is that you have this extremely accurate scale or something that goes to 4 decimal places. Like extremely accurate, like crazy. And so you're stating that, hey, this is actually, I know this is accurate to 4 decimal places, and this is exactly 1, 2, 3, 4. Accurate to 4 decimal places. That's what you're saying. If you are not able to measure with that much accuracy, and you're only measuring to the nearest maybe whole gram, you would only put those numbers. But if you want to state more precision, and you say, yeah, my scale actually goes to 2 decimal places, so here's my actual measurement, and I'm more confident in the precision of this measurement.
But if you were to add those together, you would not.
Yeah, we're going to talk more about adding and multiplying and determining calculations. That's coming later. Just save that for later, because there are different rules for adding and subtracting as there are for multiplying. But we'll talk about that later. That's coming. Right now, we're just looking at individual measurements, not calculations so far. Okay. All right, number 4. Number 4, zeros that are after the decimal point but before non-zero digits are not significant. So let's unpack that. And this one seems the least intuitive, I would say, to most people. So for example, if I have something like this, that measurement right here, these are zeros that are after the decimal point. So these zeros here, but before the non-zero digit, the number 2, are not significant. So what they are said to be are placeholders only. So this has 1 sig fig right here. 1, the 2, that's it. These are not significant. And I know that over here, they were significant, but they followed non-zero digits. So this has 1 sig fig. If I actually showed you this measurement though, guess how many sig figs this would have? 5 sig figs, you got it. So these zeros are placeholders only. If they are placeholders only, they do not count in the precision, okay? Because how else would you say that this is, 2, was it 10 times? 2 10,000s, or 2 thousands, 2,000ths of a whatever, okay? You could use scientific notation, which we'll talk again later about that, okay? But this is just 1 significant figure because those are placeholders only. So think about this one then, you're still having trouble. Watch this. Which one of those measurements do you think is more precise? The one on the right is more precise, because right now I am not showing any digits here because I am not sure what they are. I don't know what they are. My measuring tool does not tell me what these digits could be, therefore I can't show them. Over here, my measuring tool tells me that these digits are there, so I can write these zeros. Now, the next rule will talk about these other zeros, okay, after the...
But that one has 3 sig figs, right?
Yes, this one on the right has 3 sig figs. Placeholders, so they're not considered. These are part of the expression, so they...
They're not actually zeros, they're nothing.
Okay, here's another example, or that's like the example I just gave you, I guess, on your next page. So this has 1, 2, 3, 4 zeros ahead of the non-zero digits, but they are not significant because they are placeholders only. So this one has 3 sig figs here. Okay, I know, guys, you're wrapping your head around this. This is good. It's a good exercise for you. Finally, 5, zeros after the last non-zero digit but before the decimal place are not significant. So this is the last one. And again, this one too is a bit strange. Even though there's zeros after a non-zero digit, because there's no decimal place, these zeros are also placeholders only. So in this measurement of 7,000, that's 1 sig fig. Because what this is saying is that I can only guarantee that this is close to 7,000. I don't know how close it is. 7,000 is the nearest thing I can bank on. It's to the nearest 1,000.
Because the last zeros
But if you had,
number.
The last zeros are just placeholders only.
but if you had that number 0.0, then all.
Yeah, yeah. So if you had, so now, let me draw this somewhere else. So this is 1 sig fig. That is 5. Because now that you put the decimal with this, you didn't have to do that, right? But now you're saying, hey, I am actually precise. All these digits are measurable or whatever, that I'm precise to this. So this is 5 sig figs now.
Oh, because it's sig figs are only.
And this one, as I mentioned before, these ones are not significant. They're placeholders only. These zeros are significant, so this is 3 sig figs, okay? Because these zeros are after a non-zero digit and after a decimal place. So we will get lots of practice with this, okay? This is just an initial shot at these rules here, okay? Okay, so here's a practice sheet that you guys should have in front of you here now. And let me just go over some of these, okay? So let's use the rules that we've just learned and get some practice here. Okay, so Frozen, sorry. How's that? You got there now? Okay. All right, so this one is like just like the example that we did. These are not significant, these are. So this is 3 right here. 9. Still frozen? Okay. 3. This one, is that 0 significant? No, it's a placeholder only, so this is 2. Good. Now, scientific notation, we haven't talked about this specifically, but one of the reasons why scientific notation is really handy is that you can easily look at the significant figures, and they're all right here. You don't worry about this at all. It's just this. This is 2. Because the reason why is because in scientific notation, which we'll talk about more in the coming,
Oh, this is the weakest thing.
no.
Oh, wait.
This whole thing right here is a number that's written in scientific notation. I will explain scientific notation again a little bit later, but this number would be 1, 8, and then this 8 here means that this decimal place goes over to the right 8 times. So you have 1, 8 followed by 7 zeros. That's the number. Okay, 2 sig figs only. These are all placeholders, so that's 2. But we'll talk more about scientific notation coming up soon.
Should we be writing like SF after all of them?
Nope. No, you don't have to write us up. Okay, this is 3. What's this one? 2. What's this one? 3 is correct. What's this one? 4 is 1. Very good. This one?
4,
Yep, those zeros in between are significant. This one?
1.
Good. That's just 1. Those zeros are all placeholders. And obviously they're both non-zero. Okay, there you go. So go ahead and finish the rest. It should be
8, 10 is 2, right?
8, 10. Yeah, this 0 is just a placeholder only, so there's only 2 there. That's correct.